So let me just write down some of the things we did yesterday. We are looking at this definition of Boolean circuits. Yeah, so let us carry on with our discussion of circuit complexity. So we began yesterday by discussing the non-uniform model, okay, so non-uniform model of computation, where instead of requiring just one machine to be able to compute, let us say some function or something for all strings in a language, let us say we have different, we have a family of machines, or in this case we have a family of circuits which computes a language. Okay. So how do we model such a such classes, and what does that give us? So so we will assume for the time being that our circuits are single output circuits, that is they have one sink node, and they have n sources, and we will assume that we are looking at inputs of size n. Okay. So again, for the time being we will just assume that there are no constants involved. So yesterday I did say that you can have constants, you can still have constants, but what did I say? Yeah. So the n sources that you have, so let us just stick to the notation that these sources correspond to the n bits of your input string. Yes, it is not difficult to generalize this, but let us just have this for the time being. And then the size of the circuit is basically the size of the graph, in the sense that how many vertices the graph has. Okay, so how do we compute a value? Again, that is done in a very in the natural manner, but I can mention it. Yes, so when I say vertices, I mean sources as well. Right. So, yeah. So let's include sources as well, because I was. So basically, the book has this definition. So yesterday I was talking about the sources as being input gates also. So then you can talk about the number of gates, but the book, the way the book defines this a circuit is, they only call the non-source vertices as gates. So that is why I want all the vertices to be part of the size. Okay, but actually, as we shall see, all these things do not matter much. I mean, there is only a constant factor difference between these things. But okay, so what is the value? Yeah, so let x be some string of length n. Okay, so then the value computed at a vertex v, okay, we will denote it by value of v. So this is equal to xi if v is the ith source vertex. Okay. So we can assume there is an ordering among the source vertices, and the value of the ith source vertex is the ith bit of this string. Okay. So that is why we just assume that there are no constants for the time being. So value of v is equal to some value of u or value of w if v has a label or and uv and wv are the two incoming edges to v. Okay. So just one more thing that I didn't mention yesterday. So we generally refer to the in degree of gates as the fan-in of that gate. Okay. So that is again a fancy term, but in circuit complexity you might often come across this. Okay. So just I wanted to mention that. And similarly for and not also, it is defined in the same manner. It is value of u and value on w if v has a label and these are the two incoming edges to v, and it is not of value of u if v has label not and. So in this case it has fan in 1, so uv is the only incoming edge. Okay. So this is how the value is computed at each vertex given a string x, and the value of c is the value computed at the sync node. Yeah. Okay. So, this is the proper definition of a circuit and how does it compute a value. And now you can see that it is easy to generalize this to circuits which compute more than one bit of output. Okay. So, greater than 1 bit. Okay. So, basically it will have multiple sinks. Okay. So, this is the definition. So, now let us look at the class of languages that the basic class of languages that we can define. Okay. So, suppose we have some function from positive integers to positive integers. So, we say that C n is a T n size circuit family if for all n size of that circuit is less than or equal to T of n. Okay. So, basically this allows us to look at a circuit family of a certain size. Okay. So, for every n I want that particular circuit to have size no bigger than T of n. Okay. Now, we can define languages also based on this idea of size. So, let us call this class size T of n. So, and as you must already be guessing what the definition will be, so it is the class of all those languages L such that there exists a let me use the order notation here, order T n size circuit family C n such that for all x of length n x is in L if and only if C n of x outputs 1. Okay, so I will just write it here. This is denoted by C of x. So, when I say C of x, it is basically the value computed by that circuit on that input. Okay. So, yeah, so this size T n basically is the class of all those languages for which there is some circuit family of order T n size which computes every instance of length n in an appropriate manner. So, if that instance belong to that language, then it will output 1, otherwise it will output 0, and this happens for all n. Okay. So, yeah, so this is the standard way of defining this. The only thing is that now we have a circuit family. So, note that when we were defining things like d time T of n and n time and d space, what we were looking for is there exists some Turing machine, a Turing machine, right. But here the crucial difference is that no longer are we restricting ourselves. So, we are no longer restricting ourselves to just one machine or one circuit. We have a infinite family of such computational objects that is able to decide the language. So, I should have written here that for all n greater than or equal to, I can put 0 also. So, you have this circuit family n. So, there are an infinite number of circuits. So, for all n, if you look at any string of that length, so that string will be in the language if and only if that particular circuit. So, the circuit corresponding to that n outputs 1 on that input. For a particular n, there is exactly one circuit, yes. Huh? Yeah, so that is one way of doing it. So, here yeah, so that is also a good. So, instead of writing n here, I can put for all x in 0 1 star, x is in L if and only if C mod x of x is equal to 1. Yeah, I mean it is the same way of I mean I am just rephrasing what I wrote here, right. So, instead of saying this, what we can say is for all x, okay, when do I say that x is in L? According to this definition, if that particular circuit outputs 1, right. So, what is that particular circuit? In this case, it is the circuit C n where x has length n. So, I am looking at all strings x of length n, okay, because if you look at the definition of a circuit, by its very nature it can only take those strings which have a certain length and nothing else. Okay. So, that is why it is in L if and only if C mod x on x is equal to 1. So, this is just an alternative way of saying the same thing. Okay. So, now let us come back to the question that we began with. Yes, yeah.
If you say for all n greater than 0, then what will be the difference between the left side n and the right side n?
Left side n and
Size of t of n.
huh.
Then this n.
Yeah, so let's so I was a little hesitant when I wrote 0. So, let me put it as 1. I mean I wrote 1 because 0 because I did not want to exclude the empty string, but that is just one string. I mean that can be taken care of separately. I mean I can always start with n is equal to 1. It is just some function. Huh? Oh, over here, yeah, here n is just a dummy. I mean here, yeah, so maybe I should mention. So, here basically n just means that t is a function. Okay. So, this n does not play any role with the n sitting inside. Okay. So, that is so it is kind of a misnomer, but if I just write size of t, it does not quite say what t is. So, that is why we write t of n. Yeah. So, now we can define circuit families which have polynomial size, and that is written as p slash poly, and it is equal to union over all c greater than 0 size of n to the power c. Okay. So, when I say n to the power c here, this is the function that I mean, that I am looking at all those languages which have a circuit family that is no larger than n to the power c for every n. Okay. And I am taking that union over all constants. So, that is this class p slash poly. So, yeah, so what I was saying a little while earlier. So, recall the motivation that I mentioned yesterday when we started our discussion, that we are not able to show whether p is not equal to np, but what about if we relax this question? What if instead of asking there is some np language which is not computable by a polynomial time Turing machine. What if we relax and ask that can we at least show that there is a family of such circuits which is not able to compute some NP language. Okay. So, this is the class which I was talking about. Is family of well, you actually want more. You not only want a family of Turing machines, each of which is designed for a particular input, you want all those Turing machines to run in polynomial time as well. So, yeah, so this statement is actually equivalent to that, and actually we will actually come to that a little bit later today, but maybe I can mention it since you raised it. Actually, that is not very difficult. So, suppose if you have a family of circuits, okay, which decides a certain language, it is very easy to convert that into a family of Turing machines again which decide the same language, because what you can do is you can just design the transition function of the Turing machine in such a way, so that it simulates that circuit. Okay. So, whatever that circuit does, the transition function of the Turing machine just copies that behavior. If you are computing, you have your input, if you are computing AND of 2 bits, your transition function will accordingly compute the AND of those 2 corresponding bits and or not, whatever. Okay. So, that can very easily be done. So, that is why yeah, but the good thing about circuits is that there is much more structure into a circuit. I mean, see, if you look at a Turing machine, it is more like a black box sitting out there. I mean, there is one Turing machine which given an input will tell us yes or no. I mean, of course, there is the transition function that we have, but well, we do not know much about the transition function as well. But on the other hand, if you have a circuit, so this has a much richer mathematical structure embedded on it. Okay, we can actually say more stronger mathematical statements, which it is not so easy in the case of Turing machines. So, I will mention this thing in more detail while we maybe today or tomorrow, but let us see. Okay, so yeah, so before I proceed, any questions? Not really, right, because I mean, if you have a circuit, what do you mean by the time taken by that circuit? Okay, so depth basically means that what is the longest path from a source to a sink node. So, if you take the maximum over all such shortest paths, that will give you the depth of a circuit, and that is also a concept which people study, and we will also look at it maybe in a couple of days time. But generally it is size and depth which is so these are the 2 most important parameters that people study about circuits. So, the first thing that we will show, and this is also not quite this is again very easy to show, that P is contained in P/poly. Okay. So, in other words, if you have a language for which there is a polynomial time Turing machine, you can design a family of circuits each having polynomial size which will accept that same language. Okay. And I will just give the proof idea, because the actual proof we have already seen something similar earlier. So, the idea of this proof is again similar to Cook's reduction. Okay, so, where we showed that SAT is NP complete, actually SAT is NP hard. Okay. So, it is basically the same idea that is being used to prove this. So, let us quickly go through the basic steps of this proof. Actually, some things are important to note. So, what we do is, so suppose we have a language L in P, which is accepted via a polynomial time Turing machine M. So, now I want to design a family of circuits. So, given any string x, okay. So, if you have any string x, let us look at the configurations that this machine will take, the various configurations that this machine will take on this input x. Okay. So, what can we say about let us say the configuration graph of M on x? Does it have any particular structure? Yes, it is exactly. So, it is just one path, right, because from every other from every configuration you can go to exactly one other configuration, right. So, let us write down the configuration. So, let us say this is my starting configuration, this is the next configuration and so on. The final configuration is some T of n. So, polytime machine M running in time T of n. And we will also assume one more thing about this machine. So, we will assume that this is an oblivious Turing machine. Okay. So, in other words, the computation of the machine does not depend on the actual input. Okay. So, it only depends on the position of its input head. Yeah. So, these are my configurations. So, now note the following things about these configurations. So, each configuration can be encoded using some constant number of bits, okay, because what is a configuration? It is basically a state and the content of its various heads. Okay. So, that can be encoded using some constant number of bits, and for all I greater than or equal to 2, Zi is dependent only on yeah. So, only on constantly many Zj's where j is less than I. So, there are only constantly many such configurations on which it will depend. In particular, of course, it will be dependent on the previous configuration, and also it will be dependent on that configuration where the input head was last scanning that same position. And yes, if it has only one work tape, then that is the only thing, and of course, it will depend on the input head position also. So, now we have these things. So, each configuration has a constant size encoding, and each Zi can be is dependent only constantly many Zi's. So, therefore, a constant sized circuit can compute Zi given the respective ZJs. Okay. So, suppose you are given whatever are those respective circuits for all those previous ZJs, there is just a constant size circuit which will compute the value of Zi for you. Okay. So, now it is basically just combining all these circuits in the proper manner. So, combine all circuits to get the circuit for Z t of n, and if Z t of n is an accepting configuration, then accept, well I should not say accept, then I should say then output 1, else 0. Okay. But what is crucial here is that we are only looking at an input of a particular size. Okay. So, that is where we are using the fact that we have an oblivious machine. So, for different input lengths you will come up with a different circuit. Yeah. So, given x belongs to yeah. So, I should say that as well. Yeah.
So how do you show that a constant size circuit can compute Zi given the respective Z?
So, we know that Zi is dependent only on some constantly many Zj's. Okay. So, suppose there are, so suppose we assume that we have circuits for all those Zj's. Okay. So, there are circuits which are able to compute that. So, since this Zi only depends on what those constantly many Zj's are, and to represent each configuration we need only constantly many bits. So, therefore, given these values we can always decide that by using a constant size circuit, because the number of inputs to this circuit is constant. Okay. And that basically forces this also to have constant size, because otherwise you will be repeating some things, right. Yeah.
But I am not convinced with the idea that whatever we can do using a Turing machine, whatever operations you can do with the Turing machines can be replicated in a circuit of constant size. Like that assumption is
No, that I am not saying.
In this argument, that assumption is hidden that whatever you can do using a Turing machine, because
In one step. Yeah.
can be done in a circuit.
Yeah. So, that assumption is there, and so the reason for that assumption is what I am saying. So, if you look at one step of a Turing machine, okay, so suppose we are looking at just one step. So, what is happening? Basically, I am going to some Zi minus 1 to some Zi, okay, and this Zi depends on some constantly many earlier configurations. So, let us say it depends on 3 other configurations, okay, it depends on Zi minus 1 and maybe some 2 other configurations. Okay. So, basically what is the transition function now? The transition function is a function which takes 3 arguments. Okay, I mean one way to model the transition function here is, if I want to compute what the configuration Zi is, it is just a function of 3 other configurations. Now, what I am claiming is, and also what we know is that each configuration can be encoded using constantly many bits. So, now what I am claiming is that, suppose somebody provides me with the values of those 3 arguments, what those 3 arguments will be, and here I am using the fact that they have constantly many bits. So, now the circuit size that I need to compute Zi from those constantly many bits cannot be larger than constant. Okay. Because if it is large, if it is larger than some constant, then basically you can use pigeonhole principle or something like that to show that you are performing redundant information. Because if you have, let us say, a function, let me tell you a simpler thing. So, suppose if you have a function on 4 variables. Okay. So, how many different functions are possible on 4 variables? Huh? Binary functions, yeah. Okay. Not 2 raised to the power, so it is 2 raised to the power 2 raised to the power 4, right. Okay. Because for each setting of these 4 variables, so there are 2 to the power 4 settings of these 4 variables, and for each setting it can take either a value 0 or 1. So, now suppose you relax this to any k array function, where the function outputs a string having k bits. So, it will be some some k to the power 2 to the power 4, something like that. But the point is that if this is constant and if that k is constant, then this has to be a constant. So, the number of functions itself is constant. So, therefore, the size of that circuit which computes that will be constant. So, that is the implicit nature. Yeah. But the size basically blows up when you combine all these things. So, here we are assuming that we are already provided with these zj's when we are computing zi's, but how do we get those zj's? So, there is a linear chain which gets built up, and that is why when you combine all these circuits to get the final circuit. So, this will have some size, some order of T of n, because there are T of n configurations. So, yeah, so the essential idea behind this and also the Cook's reduction is that you can very easily go back and forth between this circuit model, or let us say formula whatever, and the Turing machine model. So, if you have a circuit, you can always simulate it on a Turing machine, and if you have a Turing machine, that always there is always a corresponding circuit for computing the same thing. The only difference is that since Turing machine is a uniform model, to go to a circuit model, you will need a family of circuits. So, that is the only difference. Okay. So, any other questions? Huh? So, we will look at that. No, P by poly, does it include NP? No, so that is not known. So, whether P by poly includes NP as well, so that is not known. In fact, that is not believed to be true as well. So, that is what we will probably show tomorrow. Okay. But actually it is a class which is incomparable with all these classes P, well, it is comparable with P, but it is incomparable with all the other super classes of P, such as NP, P space, EXP, and that we will see just now why it is incomparable. It is a very easy argument for that. Oh, I erased this, but so I hope everybody was done copying this part of the. Okay. So, let us look at the following language. Let us call this U empty. Okay. So, UMT is the unary encodings of all those machines M such that N the binary representation of n encodes a Turing machine M such that L of M is empty. Okay. So, those are not the yes instances. So, I will look at all those n's, okay, which are valid encodings of Turing machines and their language is phi, the language of that machine is phi. So, if you have an n which is not even a valid encoding of a Turing machine, then you do not include that in this language. Okay. So, what can we say about this language? So, again this is from a POC course point of view. Huh? So, is this language decidable? So, this is undecidable, right, and why is it so? Anything you can prove it using Rice's theorem or whatever. So, at least if let us look at the following language. So, suppose if you have the binary representation of a Turing machine M such that L of M is empty, that language is undecidable, right. So, that probably you have seen in your TOC course, or even if you have not seen, it is very easy to prove. I mean, it is very easy to reduce, let us say, the halting problem or any other undecidable problem to that problem, if you have the binary representation. What I am claiming here is that even the unary representation is undecidable, because suppose this were to be decidable, what I can do is, given a binary representation of a machine n, of a machine M, I can very easily convert it to its unary representation, right. I mean, I can easily look at a binary number and convert it to a unary number, and then I run the machine for UMT, and that will allow me to decide the other language, and that we know is not possible. So, therefore, this language is also undecidable. Okay. But what can be shown is the following, is that suppose you have any language L, okay, so maybe it is over binary symbols, but L is a unary language. Okay. So, then L actually belongs to this class. So, no matter what unary language you pick, that always belongs to P/poly. Okay. So, again the proof is actually very simple. So, any idea how we can prove this?
Just have n, and for each edge I will reject the circuit such that, or if n is accepting, then I will reject it just one, and if it is not accepting,
Yeah, basically that's, you have to be little careful in the accepting part, but basically that is the idea. So, now note that all we want is a family of circuits. So, that is for each length n, I want a circuit which will either accept or reject that input. Okay. So, what I will do is, if 1 to the power n belongs to this language L, okay, so then design C of n such that C of n computes the AND of all its input bits. Okay. And if 1 to the power does not belong to n, then design C of n that no, that is not, huh?
These inputs are just
Take
one
the
node.
one. So just take one of them's node.
Take anything and just one node.
You mean for this?
Yes, sir. Take the first input bit and wire it to a node.
I mean, you don't need, I mean, you just, I mean, you can just design a very trivial circuit which will always output 0. You don't even need to look at the input, right. So, such that output 0. Okay. Huh? No, because of this, no, because I am assuming that the language can be over binary strings. So, I can have a x which has some zeros also in it. Okay. So, maybe I have an x which looks like this 0 1 0 sorry 0 1 1 and also the string 1 1 1 is in this language. So, I do not want to accept this, but I want to accept this. So, that is the reason. Okay. Because it is yeah, so it is a unary language, so it is sufficient to take the AND of all the input bits. Over 1, yeah. Yeah, that is true. Huh? Alphabet is binary. Actually, it does not matter. I mean, I think you can also assume the alphabet to be unary, because even then this language would be undecidable. So, the whole point is that there are undecidable languages which are there in P/Poly. So, that is the whole point. So, P/Poly contains undecidable languages. Okay. Yeah. Huh. Oh, here. So, suppose you look at, so suppose 1 to the power n is in L. In particular, I am looking at n as having the value 3. Okay. So, 1 1 1 belongs to L. But since the theorem is for L, which is a unary language, 0 1 1 is not in the language. Okay. So, the circuit that I designed for C3, that should reject 0 1 1, whereas it should accept 1 1 1, and that is the reason why I am taking the AND of all bits. So, even if it has 1 0, then it will output 0, only that will be accepted. Okay. But see, this is kind of cheating in some sense, right, because I am that is not the problem. I mean, you can assume the alphabet to be unary here also, and I mean the same thing will also carry over, in which case if 1 to the power n is L, you just design a trivial circuit which outputs 1 and 0. So, that is not the point, but the cheating is in the place when we are designing the circuit. Okay. So, what does circuit family say by definition? So, we say that a language is accepted by some circuit family if there exists a circuit family. We never talk about how we get that circuit family or how to construct such a circuit family. Okay. So, we are just exploiting that freedom that is given to us by that definition in proving that an undecidable language is contained in P/Poly. Okay. So, this is something, well, I mean there can be cases where it is useful, but again this is something which we would like to restrict. I mean, we would also like to look at those kind of circuit families where the circuits are constructible in some reasonable amount of resources. Okay. So, that will make, I guess, more sense in certain cases. Okay. So, I mean certainly it will rule out this kind of a behavior. So, what do you mean? So, reductions, so if you look at polynomial time reductions, of course, P by poly is closed under polynomial time. It is closed under both polynomial time and log space reductions.
And any other bits which are more power than
You can look at Turing reduction, but Turing reduction I am not sure if P by poly is closed under Turing reductions also, but I mean we have not seen Turing reductions yet, so I will not discuss about them. But I mean I doubt if there are any other powerful reductions under which P by poly is closed, okay, because even this is not known. Okay. So, whether NP is contained in P by poly or not, so this is not known. So, this is open, okay, and in fact this is believed to be false actually. So, that is what we will discuss I guess tomorrow, that if this happens, that if NP is actually contained in P slash poly, then the polynomial hierarchy will collapse to sigma 2p, that is the second level. So, that is why this is not believed. So, I do not know if it is closed under any other family of reductions. So, yeah, it is, yeah, so it is uncomparable to NP certainly, but it is it contains P. Well, that is not again a very correct statement to make. It does not contain each undecidable language. The unary version of each undecidable language is contained in P slash poly, because if you look at the binary version of this language, that we do not know, but that is probably not true in fact. In fact, we will look at something of that flavor, I guess not today, either tomorrow or in the next class, where we will show the existence of functions which cannot be computed by circuits. So, there does exist functions, Boolean functions, which cannot be computed by circuits. So, let us look at just one more thing and then we will stop today. Yeah, so I mean how can we circumvent this problem? So, we will look at or we will define a subclass of these kind of circuits known as P uniform circuits. Okay, so what are P uniform circuits? Okay. So, a family of circuits Cn is said to be P uniform if there exists a polynomial time Turing, want n to be provided in unary. So, then what it would do is it would output the corresponding circuit C of n. So, this P comes from the fact that this is a polynomial time Turing machine. Okay. So, now we have a certain degree of restriction on the families of circuits that we are talking about. So, suppose if you have a P uniform circuit family, okay. So, suppose if you have a P uniform circuit family which computes a certain language, then what you can say is, given any input string x, first you look at the length of that string. Okay, so, suppose you have provided that string to a Turing machine, just look at what that length is, and then you simulate this machine m on 1 to the power n. Okay. So, that will give you the circuit C of m. Now, you can simulate that same input on the circuit and then you can answer yes or no. Okay. So, basically this is a more proper way of coming from languages which are accepted by circuits to Turing machines. Okay. So, in fact, I will just state that as a theorem. So, I will just leave the proof as an exercise because it is not very difficult, it is just combining the ideas that we have already seen. So, a language L is in P if and only if there exists a P uniform circuit family Cn such that L I will just write it in short, L is computed by this family. Okay. So, in other words, if you look at any string of length n and if that string is in L, then C of n would output 1, otherwise 0, the usual definition. Yeah, so I will just leave this proof as an exercise. So, suppose if it is in P, coming up with a circuit family which is P uniform. Okay. So, actually it is basically nothing, it is just so whatever the proof of that we gave earlier, that P is contained in P slash poly, you can very easily figure out that it is a polynomial time construction. So, the circuit that we computed for that language, that circuit is a polynomial time construction. Okay. So, that is the proof of the forward direction, and for the reverse direction it is just taking that circuit, taking an input, constructing that particular Cn and simulating that input on that C of n. Okay. So, I will just leave this as an exercise. Okay. So, any questions? Yeah.
Basically expecting the power of circuits to deliberately doing that to polynomial time.
Yes. Not the power of the circuits, how the circuits are obtained in some sense. Yeah, I mean it will restrict the family, I mean the class of languages accepted by such circuits. Yes.
This will be only those classes which the Turing machine can compute. If it cannot compute something, then we cannot come that circuit.
Yeah, so that is basically what this means, no. So, it is basically exactly those languages which are in P. So, not only the Turing machine can compute, it can compute them in polynomial time. So, yeah, so this is kind of a drastic restriction, but we can't help it. Okay, any other questions? Yeah. Sigma star, yes. Yeah.
This contains in particular undecidable language.
Yes.
So what is the inclusion of suggestion that something contains undecidable?
No, but this is a class of languages. So, when you are talking about sigma star is one language, okay, it contains another undecidable language as a subset. Okay, in fact, all languages are subsets of sigma star, you are right, but then decidability or any other such property is not closed under the operation of containment. Okay, so that is a very easy thing to see. But here when we are talking about P by poly, this is not one language, this is a whole family of languages, it is a class of languages. So, what I am saying is that this class of languages contains certain undecidable languages as well. So, it will be more than 2 to the power n probably.
By distinct I mean that two circuits are distinct if they accept different.
If they accept different functions, yeah, right. So, let us look at a representation. I mean, how do you represent a circuit? Okay. So, suppose you have a circuit on n variables, right. So, one way to so let us say it is a circuit of size n. Okay. So, how do you represent a circuit? So, one way of representing circuits is basically by graphs, right. I mean that is the most natural way of representing a circuit. So, now the question therefore is that how many graphs are there on a n vertices? How many directed acyclic graphs are there? Okay, and actually you have certain other restrictions as well, that is each vertex of that graph has in degree at most 2. It can have 1 or it can have 2 also. Yeah, but that will not, that is true, but that will not reduce it significantly. But even then, I mean, even with all these assumptions, actually you can show that it will have more than 2 to the power n
But there can be two
graphs.
There can be, the point was that there can be two circuits which do exactly the same.
Yes.
Exactly the same work.
Yes.
So should we consider those two circuits?
Let us say even if we consider them as the same.
Then we can also look at the input and the output only, because we are given a string and we just output 0 or 1. So we can
No, but there is a size, intermediate size, no. So see, the number of functions, if you look at this, so that is, it is not sufficient to look at that, because that is a huge number. So as I said little while earlier, if you look at the number of such possible functions, so this number is much larger. So this is some 2 to the power 2 to the power n. But the number of circuits, okay, which can compute a function on n variables, so that is probably, I mean, that is definitely not as large as this, but it is larger than 2 to the power n. Yeah, it is definitely larger than 2 to the power n, because you cannot represent a graph using n bits. If you have an n vertex graph, you need more than n bits to represent it. I mean, even if you look at, let us say, an adjacency list representation, there are n rows in that thing, but you need to have some non-trivial graph. It has, yeah, I mean m is of the order of n again, because the degree is bounded, but
m is
no, it is of the order of n, because degree is bounded.
Side will be order of n square.
Yes, so size is order. So this is clearly true. So the number of such circuit is not greater than 2 to the power n square. So it is certainly less than 2 to the power n square, and actually it is also less than probably some 2 to the power n log n or something like that. So I do not know the exact bound on it, but it is greater than 2 to the power n definitely. That can be proven. Okay, so we will meet tomorrow then.